So this is the second video of CC1. It's a paper 1 topic on states of matter, and this video will focus on heating and cooling curves and also predicting the state of a substance when you're giving melting and boiling point data. So what I've drawn out is the start of what's going to be a heating curve. So I've got time in minutes on the x-axis, and on the y-axis I've got temperature in degrees Celsius. We are going to draw the graph for heating water, and we're going to start with ice, because we're going to start here below 0 degrees. So we're going to be starting with ice, and we're going to imagine that we've got a piece of ice and that we are heating it over time. So because we are heating the piece of ice, my graph is going to be increasing on the y-axis as the temperature of my piece of ice increases. So it's going to be increasing, increasing, increasing as I heat my piece of ice. So if we think about what's actually happening in terms of particles, if you heat a piece of ice, obviously ice is a solid, so the particles in a solid are neatly arranged in a regular arrangement, and the particles are all close together. As I heat this piece of ice, the particles are going to gain energy. As a solid, the particles can only vibrate, but as those particles gain energy, they'll vibrate more and more, and eventually the particles in the solid will have enough energy to break apart, and that's when they're going to form a liquid. We call this process, when a solid turns into a liquid, melting. And for water, that's going to happen at 0 degrees Celsius. So when I get to 0 degrees Celsius, I'm going to go from a solid to a liquid. On the heating and cooling curve, however, you see a flat part of the graph when the state change occurs. So this here at 0 represents when my solid is melting. But instead of increasing the temperature of the particles at this time, you get a constant temperature just while the state change is occurring. It is not because you've stopped heating the solid. Okay, you are still heating the solid. You're applying the same heat that you've always been applying. But beforehand, the heat you were applying was going towards increasing the temperature of the solid. At the point when the solid is melting, the heat energy you're applying goes towards separating the particles to make it a liquid. Because the heat energy you're applying is not increasing the temperature at the time of the state change, you see this flat part of the graph when it is melting. After it's melted, if you continue to heat it, the temperature of the particles will continue to rise. Because I'm talking about water, it's going to keep rising, rising, rising until I get to 100 degrees Celsius, when another state change will occur. So at 100 degrees Celsius, there is enough energy in these liquid particles to fully break free of each other, and at that point it's going to become a gas. And this is called evaporating, or you can say boiling. So again, as I heat my liquid, so it's a liquid after it's melted, as I heat my liquid, the temperature of the substance is increasing, increasing, increasing. But when I get to 100 degrees, even though I'm still heating my substance, I am again going to see a flat part on my graph, and then the temperature of the particles can rise once more. And the reason I see this flat part of the graph is because, again, I've got a state change occurring. And at that point, instead of the heat energy being used to increase the temperature of the particles, the heat energy you are applying is going towards separating those particles. So you see a temporary flat constant temperature before the temperature will start to rise if you continue to heat the water particles when they are a gas. I have included this for you in your booklet. Okay, so it talks about the two flat parts of the graph. The flat part means a state change is happening, so at 0 it's melting, and at 100 it's evaporating. The flat means that the temperature of the substance is not changing, and the reason is because the heat energy is being used to separate the particles. So your typical kind of questions on this. So explain which part of a heating curve indicates a state change. It's the flat bit, and that's all you would need to say, the flat bit. It says explain though, so how do I explain that? Because the temperature of a substance remains constant, so the flat line indicates that the temperature is not changing, so the temperature remains constant when that state change is occurring. Why does the temperature stay constant during a state change? Because the heat energy you're supplying is being used to separate the particles instead of being used to increase the temperature of the substance. Okay, that's pretty much it on heating curves. The opposite of a heating curve would be a cooling curve. So I've just sketched out a cooling curve here. It's a similar idea, except instead of increasing the temperature, you're decreasing the temperature. So again, assume I've got water. I'm starting off with water as a gas, and the temperature is above 100 degrees Celsius. Then I'm removing energy. I'm cooling down this water vapor. When it hits 100 degrees Celsius, that's when the state change is going to occur. So even though I'm still cooling my particles, they are not getting colder at that time because instead they are reforming a liquid. Once I've reformed a liquid, I can continue to cool my liquid. The temperature of the liquid is getting colder and colder and colder, but when it hits 0 degrees Celsius, again you get that flat part on the graph when the state change is occurring, and then you can continue to cool your substance down. So again, the exact same idea as what we had with the heating curve, except you're cooling, you're still going to see that flat part on the graph for the state changes because the temperature remains constant during a state change. Okay, the final part of this topic asks you to predict the state of a substance if you're giving melting and boiling point data. This is typically a question that students really struggle with. So I've presented a table that has the melting point and boiling point of lots of different made up substances. And what I want to know is what state each of these substances are at 50 degrees Celsius. So I've given you the melting point, okay? This is the point at which a solid becomes a liquid, because that's what melting is. And I've given you the boiling point, which is the point at which a liquid becomes a gas. You can see that our first substance melts, so becomes a liquid at minus 20 degrees Celsius. I should cover the rest of these. The first substance melts, so it becomes a liquid at minus 20 degrees Celsius. When it hits 70 degrees Celsius, it then turns from a liquid to a gas. My question is, what state is it at 50 degrees Celsius? Well, it becomes a liquid at minus 20 degrees, and it stays a liquid until it hits 70. So 50 degrees is enough to go from a solid to a liquid. 50 degrees is hot enough to melt my substance, but it is not hot enough to boil my substance, and that means it's going to be a liquid at room temperature. The next substance does not melt until 120 degrees Celsius, so it stays as a solid until it hits 120 degrees Celsius, and you have to heat it right up to 333 before it becomes a gas. So what state is it at 50 degrees Celsius? Well, it won't melt until 120 degrees. 50 degrees Celsius is not enough to melt my solid. Therefore, if I don't have a high enough temperatures to melt my solid, then it will be a solid at 50 degrees. 20 degrees Celsius is the melting point of the next substance. So at 20 degrees Celsius, it melts and becomes a liquid, but it doesn't become a gas until 180. So 50 degrees Celsius is enough to melt. It's enough to make it a liquid, but it is not enough to boil. It's not enough to make it a gas. So it's going to be a liquid. I want you to have a go at the other three yourself. And underneath, I've written a kind of a table to help you. Okay? If the temperature that you're given is less than the melting point, it's going to be a solid. So here we saw 50 degrees was less than 120 degrees. So your given temperature is less than the melting point. Therefore, it was a solid. If the given temperature, which is 50, is between the melting and boiling point, then it's going to be a liquid. So we've seen that twice already. 50 degrees is hotter than minus 20, but colder than 70. So it's in between the two, it's a liquid. Again, 50 degrees is hotter than 20 degrees, but colder than minus 80. It's in between the two, it's a liquid. The other option, which we haven't seen yet, is when the given temperature is greater than the boiling point. So you would look at the boiling point and ask yourself, is 50 degrees hotter than the boiling point? So have a go at doing these last three for yourself. Actually, just press pause, do these three for yourself, and then press play when you're ready for the answer. Okay, so if I finish going through these, the next one, 50 degrees, I'm going to use this table. 50 degrees is hotter than minus 220. 50 degrees is also hotter than minus 65. Therefore, it's hotter than both the melting and the boiling point, which means it's going to be a gas. Okay, this substance becomes a liquid at minus 220. It becomes a gas at minus 65. And then it will stay as a gas after that. So it's going to be a gas at 50. The next one, 50 degrees is hotter than minus 80 degrees. And it's hotter than 25 degrees. So again, it's going to be a gas. If it's more than the boiling point, it's going to be a gas. And finally, 50 degrees is less than 850. So I need 850 degrees Celsius to turn this solid into a liquid. I've only got 50 degrees Celsius. That's not enough. So it's going to be a solid. And it will be this category here. 50 is less than the melting point, therefore it's going to be a solid. So these questions are typically just asked in a table, and you're asked to just fill in the state that you would expect. So I'm going to give you one more question to have a go at now. Similar style question. You're given four different elements. You're given the melting points. You're given the boiling points. They want to know what state they are at 21 degrees Celsius. You get 1 mark for each correct answer. Press pause, press play when you're ready to see those answers. Okay, so I fill them in for you. 21 degrees. It's hotter than minus 7, but colder than 59. If it sits in between the two, it's a liquid. 21 degrees, higher than minus 101, higher than minus 34. If it's above both of them, it's a gas. The next one is the same. It's above both temperatures, it's going to be a gas. The last one, 21 degrees, is colder than 114 and colder than 184. If it's colder than both, it's going to be a solid. Just one other question while we're here on our heating and cooling curve. So this is an example of a heating curve. It wants to know what is happening to the ice at stage B. Here is stage B. You can see it's at 0 degrees, and you can see that the curve is flat at this point. They want to know why or what is happening. You can say that the ice is melting, or you can say that you have a state change. Either will get you the mark. So state change is in general, but melting is naming that specific state change. Okay, there are a few more questions in your booklet that you can have a go with, but generally the questions that we've just gone through are the typical questions that you would expect to be asked on this.